share the videos. Now let me know whether you can hear the sound. Testing.
That smartphone you're holding has over 110 meters, or about 360 feet of wire.
Testing completed. Can you hear the sound of video?
Yes, sir.
Okay.
Wires inside of it. And that's what it takes to combine a camera, speaker, display, Wi-Fi, antenna, GPS, battery, fingerprint sensors, dozens of microchips, and many more components into a single device, and have all the components work seamlessly together. There is one football field's length of wire that fits rather comfortably in that smartphone of yours. But wait, where are all these wires? Enter the printed circuit board, or PCB. You've probably seen a circuit board like this one, and it may have been green, not blue. But what you may not know is that this circuit board is really a multi-layered labyrinth of hundreds of copper wires. This PCB provides structure and organization for all the components to be mounted on the surface, while wires in the middle allow each of the components to communicate and work together. So then, what's inside the printed circuit board and how does it work? First, let's establish the difference between components such as the microchips, resistors, capacitors, connectors, and the printed circuit board itself. These are the components and they are solder mounted or attached to the PCB. The term motherboard refers to a printed circuit board with the components mounted to it, whereas a PCB is just a flat board without anything on it. Certain components like the display and camera are not mounted directly to the PCB, but rather they are attached to the PCB through a set of mating connectors and a flat cable. This is an X-ray picture I had taken of this PCB. The dark areas are the conductive wires or traces, and there are a lot of them. And the rest of the material is a non-conductive insulator made of woven fiberglass with an epoxy resin binder called FR4. In this X-ray image, you can see multiple layers of wires, all on top of each other, but they are not actually touching. Okay, let's move on. Here is the main microchip in the smartphone. It's called the System on a Chip, or SoC for short, and it's mounted onto the PCB on a grid of connection points, or pads, called a ball grid array, thereby connecting the brain of the smartphone to the wires or traces that run through the PCB. There are many other pads on the PCB for other microchips, such as the memory chip and wireless chip, as well as resistors, capacitors, and other components. Let's focus on a small set of wires. These 15 traces connect the SoC to the 16 megapixel back camera, whereas these 10 traces connect the SoC to the 5 megapixel front camera. The higher number of traces allows for more data to be sent. Note that each of these traces is electrically separate and cannot touch any other trace. Here we have these 32 wires that are routed along the edge of the printed circuit board and connected to a flat cable that goes to the touchscreen display. All these tiny signal wires must be routed through the PCB and fit within a width of less than 1 millimeter. In summary, the PCB, or printed circuit board, allows each of the components to communicate with the system on a chip, or SoC, and other microchips via hundreds of wires and rather precise organization. So then, what is the printed circuit board made of? Well, this smartphone's PCB is actually built of 10 conductive layers. Let's go through them quickly. The top and bottom layers are used for mounting components and acting as multiple antennae. Also, each of these components on the circuit board needs power and ground, and the PCB has entire layers that are dedicated to just that, and are aptly named the power planes and ground planes. Additional ground planes are used as electromagnetic shielding and heat dissipation. The remaining four middle layers are used to carry all the communication traces or signal wires. Each of the conductive layers is composed of copper, and between each of the layers is an insulating fiberglass and epoxy resin that prevents the flow of electricity. This PCB has 10 conductive layers. However, in other applications they can have anywhere from 2 to 50 or more layers, but most PCBs stay around 2 to 10. Additionally, on the top and bottom is a coat of colored solder mask, which provides electrical insulation while keeping the mounting pads for the components accessible. And on top of that is silkscreen, which is just ink used for markings and letters that tell where components are placed. Let's jump out of animation. Hi, I'm Teddy and I'm the creator behind Branch Education. Let's take a short break from all this technical jargon and slow down and chat. I think it's truly amazing that 50 years ago computers took up entire rooms and looked like this. And now after decades of really hard engineering and development, we have something this light, small, and thousands of times more powerful, and everyone has one of these in their pocket. Our world is amazing, but these innovations were only made possible because of the hundreds of thousands of scientists, mathematicians, and engineers that studied hard and then worked even harder to discover and design transistors, microchips, and PCBs, while shrinking the size of each one of these by factors of multiple thousands. So here's my pitch. If you want a future full of even more amazing innovations, then you should take it onto yourself and pursue a career in science, technology, math, or engineering. But if you can't do that, another way you can help is by liking and then sharing this video. And maybe it will inspire some student out there to pursue a science. Thanks for watching and helping out. Okay, now let's get back to the PCB and the thousands of microscopic wires inside of it. So where were we? Okay. With 10 separate conductive copper layers and insulating material between each layer, how do signals travel from one layer to another? Well, vias, or vertical interconnect axes, perform this function. You can see them in the X-rays here. Vias are drilled and metal-plated holes that connect 2 or more layers. There are 3 types of vias. Through vias are holes that go from the top to the bottom layer. Blind vias connect either the top or bottom layer to a middle layer, and buried vias connect internal layers to one another. Because vias can pass through multiple layers, when they pass through a layer that they don't want to connect to, the copper is removed from around the via on that layer. Let's take another look at an X-ray of a very small portion of this PCB, and then let's zoom in even further on this X-ray. Here are the pads on the top side of the PCB for mounting components, and on the inside you can see a set of wires running this direction, and then another set of wires running perpendicular to that direction on a separate layer, and a third set of wires running at an angle, while vias go between each layer. Here's a dime so that you can get a sense of scale for the size of these wires. These intricate wires found inside the PCB at the center of your smartphone are just mind-blowing. Okay, let's move on. Each model of smartphone is different in shape and specifications, and thus each has a different printed circuit board, which engineers carefully design. For example, some smartphones separate the top and bottom PCBs, with the bigger one called the motherboard and the smaller the daughter board. Or for another example, some newer smartphones stack PCBs on top of one another in order to fit more space for a larger battery and more cameras. Another important detail is that this PCB is light and small. It weighs just shy of a tablespoon of water, and well, it fits inside your smartphone. Engineers have been continuously innovating, making microchips, resistors, capacitors, inductors, and connectors as small as possible. Some of these components are smaller than a flea. Older designs of PCBs used components that took up much more space, both on the board and through the board. Due to their mounting mechanism as a leg going through a hole, these older designs were called through-hole components. However, these components here are all surface mount devices, or SMD, and engineers are continuously developing smaller and lighter solutions. I'm telling you, one of you will be the engineer to design the next generation of electronics. So let's summarize and wrap this episode up. Printed circuit boards are integral to all electronics, and they come in a whole variety of shapes and designs. They provide structure, nice, neat, organized homes for all the components, and they also connect the components using a vast labyrinth of over 100 meters of wires in a connect-the-dots-like fashion. That's about it for this episode. Thank you for watching. Consider subscribing, and if you learned something new, make sure to hit that like button. But more importantly, share this video with others, and hopefully it will reach the student, or more likely a group of students.
Okay, probably you might have got the insight of a modern day PCB. There is not just one layer or two layers on the top and the bottom. There are going more than 50 layers inside a PCB. So if you look next time to the motherboard, you can see that the motherboard is not having only two layers, but probably there might be 40 to 45, maybe probably 60 layers, where all the connection and the connecting wires are running here and there. The important part is whenever current is flowing through the wires, we will have electromagnetic interference, and the best solution to have the shielding in between those interferences is provide extra planes, ground plane, okay? Ground plane and power plane in between those running wires, current running wires. We do have different types of vias as well, okay? And manufacturing PCB of this kind is not a one night development. So whenever we see that PCB manufacturing, it is always guided by some sort of rules and regulations, and these rules and regulations are based on the experience, based on the mathematics of resistances, capacitances and inductances. Okay, and this is what we are going to listen in the second video, and that second video is about your IPC standards. It is a 5-minute video, but hell lot of documentations and rules, set of rules and regulations. Let us go through this second video. I will start.
A very good day to you. And this time round in our session, we're going to talk about essential PCB design using IPC standards.
So whenever say that we have certain standard, okay, so it actually frames the rules and regulation on the international basis. So it won't happen that a PCB manufactured in China is not compatible with the devices in the US. So you do have lots of standardizations which are actually defining what should be the diameter of the component leads, what should be the dimensions of the SMD packages, what should be the minimum track or trace width for particular power, okay, particular specifications of voltages and currents. So you do have all this set of regulations, okay. Let us go.
This is a 3-day course, and in this course, we will be focusing on introducing IPC standards to our customers and participants who have little or no knowledge about what are these things. So first thing is, one of the most simplest way to discuss about IPC standards is this performance class 1, 2, 3, which is in this course we will let you know like how can you specify different performance class to your vendor in order for them to fab the board, assembly, test, and qualify the boards. At the same time, in the course, we also are interested to look at level ABC. And we find that a lot of time, customers sometimes are confused about the difference between class 1, 2, 3 and level ABC. As in, what's the difference? Do we have to qualify level ABC? Actually, the answer is no, because level ABC is for manufacturing communication purpose.
I forgot to mention the full form for IPC, that is Institute of Printed Circuits, okay, printed circuits. Then later on, it increased its scope of operation, and then we do have Institute for Interconnecting and Packaging Electronic Circuits as well. So they provide the standards for components, they provide the standards for PCB designing, manufacturing, assembly, and then soldering. Uh, they do design standards for testing your design as well. We do have lots of test benches where we can test our designs. Okay, manufacturing products. So this is what IPC do, and let us go ahead in the video.
Purposes only, and sometimes they just means that it's the tolerance involved. Like for example, level A means that it is easier for you to fab the board. So sometimes customers do tend to get confused, and they tell us that, oh, their customers wanted to uh, QA or QC level A, which is not possible. All right. So in this course, we make a very clear explanation on how you can use it properly. Right. After getting to know introduction about the IPC standards, the next thing we will go through is we will show you video sessions. The video sessions will involve how you manufacture a multi-layer PCB board, as well as we will show you the SMT assembly process. So in the video. So in this case, it's much easier for you to imagine what it is like by looking at the video, and then we discuss the important points regarding manufacture, assembly test. And then the last item we have is design for reliability. And this topic here is whereby many of the customers are very interested, because sometimes, just take for example, our customer can come from an ATE environment, and in ATE testing environment,
ATE is automatic test equipment. Okay, there is whole different uh, products which provide us automatic testing. Once I had been to Manali, where we visited a company whose product was electronic metering. Okay, and another company whose product was CFL tubes. So for electronic meter company, they had their ATE equipments in an area. You can visualize area of our department on the 6th floor. That is a huge area. Okay, they have their ATE equipments and they do have their products, and lots of people are testing. So even if we say that automatic test equipment, that really doesn't mean we are reducing the manpower. We do require the manpower to handle the equipments. Okay, so automatic test equipment is very important, and those do provide easiness of testing the products on different attire. So I can say that assembly, soldering, reliability, functioning. Okay, everywhere we do have testing.
they are very interested in reliability, but because the board, the PCB board or the test board has to go through extreme temperature. So they need to design such that the board uh, will be able to sustain the high temperature cycling without failing too fast, right? So in this kind of design for reliability, we normally have a recommended checklist, and the checklist will have, for example, we introduce you on how you can select the components based on packaging. Board materials, like what sort of board materials will have better quality to handle extreme temperatures or shock and vibration. And then we talk about stack up configuration, aspect ratio of PTH, the term
Stack up configurations means how many layers you want to have. Okay, each and every layer may be made up of different materials depending upon the functionality what you require. Okay, then aspect ratio is something related to the dimensions of the PCB in reference with the components.
thermal impacts that you get, as well as solder joint. And the last item, the LAMP pattern, which is most of our customers are interested, because the lamp pattern will actually affect the solder joint quality. So lamp pattern is actually driven by process and also driven by application. So this is where, we discuss design for reliability in a lot more detail, and then with respect to the IPC standard. At the same time, in this course, we also add in something which most of the designers these days have to know, which is the signal integrity introduction. So common things like impedance design, right? How you can lower the impedance, or how does crosstalk are being reduced, etc.
Very simple solution which you know about lowering the impedance. We know that for an ideal circuit, we require high input impedance and lower output impedance. So how to reduce the impedance? Solution, the easiest solution which we know is put a low resistance resistor, okay, low value resistor in parallel to that high value resistor. So equivalent is lower. Okay, so two resistors comes into parallel. How to reduce the crosstalk? One, we know we introduce the ground plane which provides the shielding. Never put your lower frequency traces and the higher frequency traces near to each other. Try to have the cross section area more, okay, so that will reduce the resistance. To reduce the lead lag, we have to choose the component values, capacitor component values and inductor values. We very few times play with the inductances, but we adjust lots of capacitances. Those are called as coupling and decoupling capacitances, so that we can isolate the interference in between the two parts of the circuit. Okay.
Etc. So topics like this are much in demand, but here we give you an overall introduction, and hopefully that with this information you will find that you can apply to your.
Okay. The intention of showing this video, in our syllabus we do have IPC standards for PCB, that is a short note, okay, and rest of the points are also covered in this unit in PCB design in different way, okay, in different ways. So for you, I am done with notes for unit number 4, and we do have fundamental definitions. Okay, what I will do, I will put everything in the minimized state and we will go what we do have. Okay, so we do have lots of things going over here. This is the syllabus. Okay, so we do have fundamental definitions, then standards, then printed circuit boards basic, then routing topology configurations, how we are going to route our data, that is your multi-layer, and how that multi-layer stack up assignment is done. Then we do have different grounding methodologies in the PCB, aspect ratio, and which defines the distance between the ground connections as well. Then image planes, those are nothing but your power plane and ground plane. Then functional partitioning, we can partition the PCB design depending upon the functionality of different parts. Then critical frequencies, if we are having microwave frequency, that is gigahertz clock running inside your PCB, we have to think about it. Also, we have to think about the frequencies which are going to create the interference, which are going to create the crosstalk. Okay, for handling the critical frequencies, we do have bypassing and decoupling capacitors. Then we do have different design techniques, a set of rules or thumb rules for ESD protection, that is electrostatic discharge protection. And last one is guard band implementation, how we can protect the interference in between the signals running through parallel tracks. So we do have explanation for each and every point, and we do have diagrams associated with them. So on the day first of starting unit number 4, we are ready with the notes. what I am going to do, I am going to float these notes. Okay, a link for unit number 4, and you start preparing your notes. Do remember that whenever I am preparing the notes and I am sharing it with you, those are in a broader sense. Okay, those are in the broader sense. This is what I was talking about. Okay, the notes. So whenever I prepare the notes, those are in the broader sense so that everyone do understand, shall understand the topic. And ऐसे होता है बहुत बार कि किसी किसी को पहला पैराग्राफ समझ में नहीं आता लेकिन they do understand the second paragraph. Some of the students do understand first and they really don't find the second paragraph interesting. But in a different way, I have to put down the understanding. So there is a lot of chance, you do have chance to curtail down the discussion, to cut down the discussion and prepare your own notes for your own understanding. Okay, so you have to read the complete notes, and you have to prepare your own micro notes, whatever you say. Okay, so I will share this unit number 4 notes with you, and you start preparing your own micro notes for them. Okay, so we do have discussion for guard bands. Okay, we do have discussion for design techniques, we do have in discussion for bypass and coupling, decoupling capacitors, then about critical frequencies, then functional partitioning, how we can partition. The best example is your motherboard, computer motherboard. Then image planes, how we can uh, differentiate different paths and parts of your PCB. Then aspect ratio, then grounding methodology, what we have to consider. We already studied the single point and multi-point grounding, and we are going to revisit them. Then we do have layer stack up assignments, how we are going to layer up our design. Then routing topologies, how we have to design our tracks, where we have to put them in the parallel and sometimes we need to put them in the perpendicular direction. We are saying perpendicular direction. Okay, we are not saying perpendicular to each other. Means one track is going to float on the top of another track, but they don't have any physical connection in between them. Then PCB basic a little bit. Then we have PCB standards. Okay, class A, class B, and those things, and few other fundamental definitions about electromagnetic interference and susceptibility and immunity of the signals flowing through the tracks. Okay, that's all for the today's session. This was the starting of unit number 4, where we discuss about the view of unit number 4, what we need to think about, what we are going to study. Okay, that's all for today's session, and we are done for this lecture. Thank you everyone for your attendance and presence. Thanks a lot. Bye bye.